Hello and welcome. My name is William, and today we're talking about sparse tables, a niche data structure with a great time complexity when answering range queries on static arrays. All right, let's talk about the type of situation you might want to use a sparse table. So sparse tables are all about doing efficient range queries on static arrays. So the typical use case is when you're dealing with, say, an integer array that has immutable data that does not change. Some common types of range queries that you often want to know are things like finding the minimum value in a certain range, maybe finding the sum of all the values in a certain range, or the product of all the values in a given interval, etc. So I want to give you a brief intuition on how a sparse table works at a high level without getting into too many details. So if you think about any positive integer, you know that it can easily be represented as the sum of powers of 2 given by its binary representation. For example, the number 19 in binary is 10011, which is equivalent to 2 to the power of 4 plus 2 to the power of 1 plus 2 to the 0. Similarly, we can break down an interval with a left and a right endpoint into ranges which are all lengths that are powers of 2. For instance, the range between 5 and 17 can be divided into the following 3 ranges: 5 to 13 non-inclusive of length 8, 13 to 17 non-inclusive of length 4, 17 to 18 non-inclusive of length 1. Now imagine we want to do a range query on the interval 5 to 17, and we had already pre-computed the answer for all intervals that are powers of 2. Well, we could pretty rapidly answer that range query, right? Well, that's the direction we're headed in. So we can answer numerous types of range queries with a sparse table. However, all range query functions need to meet some certain prerequisites in order to be compatible with the types of aggregation and combination operations that we want to do while building the sparse table and also while performing range queries. The first prerequisite is that the binary range combination function is associative, which means that the order in which operations are performed does not matter. If your range combination function is associative, then you can do range queries on a sparse table in logarithmic time. We will look at this in more detail later on. Now, even though logarithmic time range queries are really good, we can actually do even better. When the range query combination function is what I call overlap friendly, then range queries can be answered in constant time, which is just truly amazing. By overlap friendly, I mean that the function yields the same result whether you're combining ranges which overlap or those that do not. We can also define the concept of an overlap friendly function in a more rigorous way. A binary function f of x, y is overlap friendly if combining a with b, then b with c, and then combining the result of the two is the same as individually applying the binary function to each adjacent element pair in a sequence. Let's see an example. Suppose we have this array of values and a summation function f of xy which just adds x and y. Unfortunately, this function is not overlap friendly, and I can easily show you why. Here I have already computed the sum for 3 arbitrary ranges: range 1, range 2, and range 3, denoted as R1, R2, and R3, which we can use in the formula I presented earlier. What we're trying to test is whether our function is agnostic to the middle interval R2. First, we can pass the 2 leftmost intervals into the left side of the function, and then do the same thing for the 2 rightmost intervals. After computing the result, and the result of combining each interval individually, you see that we get different answers. What ends up happening in this case specifically is that the summation function double counts the middle interval twice. Therefore, we know that our function is not overlap friendly. So here are a handful of functions I made up. Take a moment and identify which of them are overlap-friendly functions and which of them are not. Feel free to pause the video. I left the functions which are overlap-friendly highlighted and grayed out the ones that are not. The central idea behind a sparse table is to pre-compute the range query answer for all intervals of size 2 to the x to efficiently answer range queries between a left and a right endpoint. The main downside to this approach is that you need on the order of n log n memory to store all the intervals, but in the end you end up reaping the benefits with fast queries, so that's a trade-off you need to make. To get started, we're going to need to know two variables, n, the size of the input array, and 2 to the p, the largest power of 2 that fits in n. We can actually calculate p as the floor of the base 2 logarithm, which actually turns out to be more important than 2 to the power of p itself. So after that, we can initialize a table with p plus 1 rows and n columns. Next up, we can fill the first row with the input values. The input values simply consist of the values in the original array we want to do range queries on. In this table, each cell I, j represents the combined answer for the range j inclusive to j plus 2 to the I non-inclusive in the original array. For example, the cell at row 2, column 5 represents the answer for the range 5 to 9 non-inclusive. If we are building a sparse table to calculate minimum range queries, then the blue cell would have a value of 3. However, if we're building a sparse table to do range sum queries, then the blue cell would have a value of 20. So the value in the blue cell will vary depending on what you're trying to accomplish with the sparse table. On this slide, the blue cell at row 3, column 2 represents the answer for the range 2 to 10 non-inclusive. While on this slide, the cell at row 1, column 7 represents a much smaller range of 7 to 9 non-inclusive. Now, what do we do about the cell at position row 2, column 10, which represents the range 10 to 14 non-inclusive? This interval reaches outside the bounds of the sparse table. Well, we don't need to consider partial ranges, so we can actually simply ignore this cell and all other cells with invalid intervals. Now that we understand what each cell represents, let's build a sparse table to support minimum range queries. To do min range queries, we will first need a range combination function to combine the cells together. For a min sparse table, the range combination function simply takes the minimum of the left and the right interval. The way we're going to build the table is by reusing already computed range values of previous cells. We know that the current cell at position I, j represents the interval from j to j plus 2 to the I non-inclusive in the original input array. You will notice that the interval for each cell always has an even length. This means that the interval for the current cell can easily be broken down into a left and a right interval, or rather a left and a right cell. Suppose we want to know the value of the blue cell. To compute its value, we would take the minimum of both the red cells, which represent intervals of length 4, which combined together cover the same range as the blue cell would. In turn, the red cells are computed from green cells, which represent intervals of size 2. And those are based on orange cells, and so on. In the end, the blue cell would contain the minimum value for the entire range covered by the orange cells highlighted in the table. We can finish filling the sparse table by combining values from the previous rows. So here we would take the minimum of 4 and 2, and here the minimum of 2 and 3, of 3 and 7, and so on for the rest of the row. On the next row, we would do the same thing, but now we're constructing all intervals of size 4 instead of all intervals of size 2. And lastly, we would build the bottom row, which represents all intervals of size 8. Great, we are finished building the minimum sparse table. Now suppose we want to know the minimum value between index 1 and 11 inclusive. Of course, we can look at the original input values and scan all the items until we find the smallest one. But how do we leverage the sparse table to help us? Well, in the table, we have already pre-computed the answer for all intervals of length 2 to the power of x. Suppose that we know the value of k, the largest power of 2 that fits in the length of the range between L and R, the left and the right endpoints, respectively. Knowing k, we can easily do a lookup in the table to find the minimum between L and R by splitting the range L to R into a left and a right interval. The left interval consists of the range L to L plus k, and the right interval consists of R minus k plus 1 to R. The left and the right intervals may overlap, but this does not matter given the overlap-friendly property of our function, so long as the entire range is covered. As an example, the left interval here would be between 1 and 8 inclusive, and the right interval between 4 and 11 inclusive. As you can see, the entire range between 1 and 11 is covered, and there is an overlap section. So if you take the minimum of both the blue cells, we can conclude that the minimum value between the range 1 to 11 is -1. Let's take a step back and look at how we actually found the values of the left and the right cells. The first thing we want to do is get the value of p, the exponent on the largest power of 2 that fits in the range 1 to 11 inclusive. Finding p is the same as taking the floor of the base 2 logarithm for the length of the interval. Once we know p, we can calculate k, which is just 2 to the power of p. Knowing the values of p and k, we can do a lookup in the table for the left and the right interval ranges. Intuitively, p corresponds to the row in the sparse table, and k corresponds to the length of the largest power of 2 that fits in the range, which is ultimately used to calculate the offset for the right cell. Let's do another example. Can you find the minimum value between 2 and 7 inclusive in the original array using the sparse table? Pause the video if you need more time. You can break it down into a few steps. First, find p, which is the floor of the base 2 logarithm of the left and the right endpoints. Then compute k, which is 2 to the power of p, and finally do a lookup in the sparse table for the left and the right interval values. Let's do one more example in case you want the extra practice. What is the minimum value between 3 and 5 inclusive? So you can do the same thing, find the value of p, then find the value of k, and then do a lookup in the table and take the minimum of both blue cells. As you may have realized earlier, some functions such as multiplication and summation are associative, but they are not overlap friendly. Luckily, a sparse table can still accommodate such functions for range queries. However, the runtime will be logarithmic instead of constant. The alternative approach to performing a range query is to do a cascading query on the sparse table. You can do this by breaking the range L to R into smaller ranges of size 2 to the power of x, which do not overlap. For example, the range between 2 and 15 inclusive can be split into 3 intervals of lengths 8, 4, and 2, which are 2 to 10 non-inclusive, 10 to 14 non-inclusive, and 14 to 16 non-inclusive. Let's have a look at an example. Suppose we have an input array with 7 elements, 1, 2, minus 3, 2, 4, minus 1, and 5, and we want to find the product of all the elements between the indices 0 and 6 inclusive. The first thing we want to do is construct a sparse table using the multiplication function to obtain the following table. So if we are querying the range 0 to 6, we want to break it down into powers of 2. We can do that by fitting the largest power of 2 that we can starting at the left endpoint, and then with the remaining interval fitting in the next largest power of 2 in there, and so on. So the interval between 0 and 6 can be broken down into the intervals 0 to 4 non-inclusive, 4 to 6 non-inclusive, and 6 to 7 non-inclusive. Notice that all those ranges have lengths which are powers of 2. Once you know the intervals you'll be querying, you can do a lookup on each of those intervals in the sparse table and then multiply them all together. For this example, we would do a lookup in the table at row 2, column 0, corresponding to the interval between 0 and 4 non-inclusive, the cell at row 1, column 4 for the interval 4 to 6 non-inclusive, and finally the cell at row 0, column 6 for the interval 6 to 7 non-inclusive. Once we multiply all those together, we get the value of 240, which is indeed the product of all the elements in the array. Let's do another example. Suppose this time we want to find the product of all the elements in the interval between 1 and 5 inclusive. First, we would break down the interval 1 to 5 into 1 to 5 non-inclusive and 5 to 6 non-inclusive. After that, we would do a lookup in the table for both of those intervals. The first interval between 1 and 5 is found at cell row 2, column 1, and the second interval between 5 and 6 in the cell at row 0, column 5. The product of those two cells is 48, which is the value you would get by multiplying all of the elements in the range 1 to 5 inclusive. Alrighty, let's take some time and look at some pseudocode. Let's dive into how we would implement a sparse table. The first thing you need to know is n, the number of elements in the input array. From n, you can compute capital P, the floor of the base 2 logarithm of n. This will be the number of rows in the sparse table. For convenience, I'm also computing a quick lookup array for the floor of the base 2 logarithm for all values between 1 and n. Later, we're going to want a way to quickly look up these values in an efficient manner, so I'm doing it now. The variable dp is the sparse table with p plus 1 rows and n columns. This next variable is actually pretty interesting. So sometimes it's useful to keep track of the index of the minimum or the maximum element in a range that we're querying rather than the value itself. In fact, I would argue that the index is actually more important because it gives you more information than just knowing what the value you obtain from the range query. Unfortunately, knowing the index value of the range query doesn't always make sense for all range query types, like a sum range query or a product range query, but it does make sense for min and max range queries. We can keep track of the index of the minimum element in an index table, which has the same dimension as our sparse table. Now, here's the function that builds the sparse table. First, compute n and p. N is just the number of elements in the input array, and p is the floor of the base 2 logarithm of n. Then populate the log2 array with the values for the floor of the base 2 logarithm from 1 to n inclusive. Then the next thing we want to do is populate the first row of both the sparse table with the input values and the index table with the indices 0 to n. Next, these two for loops iterate over all the cells of the table while making sure not to consider intervals which go outside the bounds of the table. After that, we can find the values of the left and the right cells and take the minimum. Lastly, we want to save and propagate the index of the smallest element inside the index table so that we don't lose track of it. You can think of the index table as an identical sparse table that keeps track of index values instead of minimum values. Once the sparse table is built, we can start doing range queries on our array. This first method finds the smallest element in a range L to R inclusive in constant time. To do this, first calculate the length of the range and find the value of p, then simply do a lookup to get the left and the right cell values and take the minimum. The left cell is found at row P, column L, and the right cell is found at row P in column R minus K plus 1. Here, K is just calculated dynamically as 1 shifted by P for simplicity. And this function at the bottom is the cascading min query function, which also finds the smallest element in a range L to R inclusive, but does so in logarithmic time. You can easily adapt this function to support range query functions, which are associative but not overlap friendly. To find the minimum value, start by assigning min_val to positive infinity. Then this next loop finds all the powers of 2 that fit within the interval. Each iteration I do a lookup in the log2 table to find p. P is useful because it can tell us the next largest power of 2 that fits in the current range length between L and R. Each iteration I shift the left endpoint by 2 to the power of p. And of course, while we're doing all this, we need to compute and return the minimum value found when considering all non-overlapping ranges. The last method I want to take a look at is the min_index query function, which returns the index of the minimum element in the range L to R inclusive. If there are multiple smallest elements, the index of the leftmost one is returned. To do this, we're basically going to do the same thing as when we were finding the minimum query value. We're going to find the values of the left and the right cell, but rather than returning the minimum of the two, we're going to compare them and find the smaller one and then return the index stored in the index table. Awesome, that's all for this video. This video was made possible by all collaborators who reviewed the slide deck, so a huge shout out to them for their contribution. Hopefully you learned something in this video, and guys, please subscribe for more mathematics and computer science videos. I'll catch you next time.